Hello friends, today we will discuss about colligative properties, which is a very important topic of class 12 chapter number 1 solutions. So before we start colligative properties, who don't know or those who have not revised water concentration terms, please watch the first video which deals with concentration terms, in which I have discussed about molarity, molality, mole fraction, etc. So, in order to understand colligative properties properly, you must be thorough with the mole fraction and molality. So, colligative properties, the basic definition is properties which depend on the number of solute particles. This part is very important. Number of solute particles, not on the nature. So they only concern about number of solute particles. So even if it is 1, 2, 3, 4, 5, 6, 7, very small number, and we have three big particles. So colligative property is concerned with number only. So whatever value of colligative property is, it will change according to number of particles, not as per the size or nature of the particle. So various colligative properties are, before we start, again this is very important, colligative properties are defined for dilute solutions only. So dilute solution means in which solute is very small, in means in present in very small quantity in comparison to solvent, because we will be doing some approximation where we will be eliminating the concentration of solute. So that is why this assumption is important. It is defined for dilute solutions of non-volatile solutes only. So various colligative properties, these four properties we will discuss in detail. First is relative lowering of Vapour pressure. This we already discussed in Raoult's law. And second is elevation or increase in boiling point. Third is depression or decrease in freezing point. And the fourth one is osmotic pressure, in which we will begin with osmosis first, then osmotic pressure. Okay, so just imagine a situation. So this is an image. So you can see from one side of this median on the road, there are a lot of bikes and cars, small vehicles are there, whereas on the other side we have large number of buses, means big size vehicles. Okay, so if I assume, let us assume mass is same on both sides. Mass is same both sides, but so even if the mass of the vehicle is same, the traffic depends upon number of vehicles. That means that is what colligative property, number of vehicles. So when we say uh, traffic is more, or traffic is high on which side, so obviously it is on left side, because it is number of particles, number of vehicles present. Similarly, colligative property, they also deal with number of particles, not on the size or nature of the particle. So number is important. Okay, just same one more example. So similarly, in a solution, I have 180 gram of solute, any solution, just example. So in any solution, I have 180 gram of solute. So urea, its molar mass is 60, whereas glucose and its molar mass is 180. So if mass is 180 gram, so urea will have three particles, because 60 into 3, 180, whereas glucose will have only one particle. Urea is having three particles. So which of these two, solutes will have high impact on colligative property? So obviously this one, because colligative property deals only with number. I hope it is clear. So that is why it is written. Urea produces 3 times as many particles. So it causes approximately 3 times greater depression in freezing point and 3 times higher elevation in boiling point and osmotic pressure. So we can summarize colligative properties in one line. Colligative properties counts heads, not weight. Okay, so with this we will begin with the first colligative property. One more thing, this we will be able to understand after this completion of four properties, but you will realize this thing. Colligative property it varies inversely with the molecular mass and molecular mass of solute, not to forget. So colligative property, they vary inversely with the molar mass or molecular mass of the solute. So again, I will tell you how to, you will be able to deduce it. So let us begin with the first colligative property, which is relative lowering of vapor pressure. So we have discussed relative lowering of vapor pressure. According to Raoult's law, the relative lowering of vapor pressure is equals to the mole fraction of the solute. This is the statement of Raoult's law. That means if I have to write it in mathematical form, I can write P naught A minus PA divided by P naught A. This is relative lowering of vapor pressure, which is equals to what? Mole fraction of B, that is psi B. Before I start, so even I told this thing in a concentration term also, but WB will represent mass of solute. Mass of solute. WA is, A means solvent, so mass of solvent. Similarly, Na is what? Number of moles. If it is A, that means it is of solvent. Nb is number of moles of solute. Okay, so what is left? Ma and Mb. So MAA means it is molar mass of, again A means solvent. Mb, this is very important because we have to calculate Mb in every case. So Mb is what? Molar mass of solute. So Mb, we have to calculate Mb probably in every second or third question. So molar mass of solute. So same thing. Now when I'm writing Xb, that means it is mole fraction of solute. So this is the statement of Raoult's law. Okay, so from here I can write Xb can be represented as, what is Xb? So I can write Xb as number of moles of B divided by total moles Na plus Nb, because mole fraction is what? Number of mole of a particular component divided by number of mole of total component. So now Na, Nb can be represented as number of moles of solute. Number of moles are what? Given mass Wb by molar mass Mb. Similarly, Na can be written as Wa by Ma plus, again Nb can be written as Wb by Mb. So I'm just putting these values. So it should be clear to everyone. Okay, so again from you can write that from equation this value is equals to this part. Okay, because we are writing everything is same till now. Okay, but in the previous slide I said colligative properties are defined for a dilute solution. Dilute solution. And dilute solution means what? Solute means solute concentration is very small. So in this denominator part, we will eliminate this Wb by Mb. Why? Because Wb is what? Weight of solute. So in comparison to Wa, that means number of moles of A, this Wa is very small. So we are writing Wb upon Mb is very less in comparison to Wa by Ma. So we are, hence we will neglect this value. We will neglect this value in denominator. So what I can write from here again? So I can write P naught A, same expression, P naught A minus Pa divided by P naught A is equals to. So now if I remove this part from this equation, so I can write Wb by Mb, and in the denominator I can write Wa by Ma. So which, when if I rearrange it, so I can write Wb into MA divided by MB into WA. Okay, so up to this point, there should be no confusion. Okay, so what we are actually going to calculate in every case, we have to calculate molar mass of the solute. So when we have to calculate molar mass of the solute, so when we rearrange this equation, so take MB to this side and put this value, relative loading of vapor pressure, in the denominator. So what expression we will get is MB is equals to WB into MA divided by WA, and this entire value will be in denominator. So WA into, now P naught A minus PA, I am writing it as delta P. So delta P divided by P naught. So this is the final expression that we have for this colligative property. So again, one relation which you can derive. MB is what? Molar mass of the solute, and this part is what? Colligative property. So you can see colligative property and this molar mass are inversely related. So colligative property is inversely related to the molar mass of the solute. That's what I told you in the first this slide. So you will be able to analyze this thing in every colligative property. So this expression is the final expression. MB is equals to WB into MA divided by WA into relative loading of vapor pressure. Okay, so now let us quickly solve one question. So vapor pressure of pure solvent. Pure solvent means what? Wherever it is written pure, that means it is P naught. So P naught is given is 23 point this mmHg. Okay, so 50 gram of urea. Now urea is what? It is a solute. So that means 50 gram. WB is 50. And this is given NH2CO NH2 in order to calculate molar mass. So MB will be this one. It is dissolved in 850 gram of water. So value of means amount of solvent is also given. That means WA is what? 850. Calculate the vapor pressure of the water for this solution and its lowering. Okay, so let us calculate it quickly. So the very first thing, in order to calculate relative loading, we need to calculate number of moles. So number of moles of water, if I have to calculate number of moles of water, so what is the amount of water given? So it is 850 gram of water. So 850 divided by molar mass of water. So when you divide it, it will approximately come out to be 47.22. Okay. Similarly, we can wait. Similarly, we can calculate number of moles of urea also. So number of mole of urea can be calculated as this amount of urea, which is 50 gram. It is written 50 gram. So 50 divided by molar mass of urea. So when you calculate molar mass using NH2CO NH2, so it will come out to be 60. So 50 by 60, it is 0.83. These are the number of mole. So Na इसको हम लिख सकते हैं Na, because it is number of mole of solvent, and it is Nb. So you can also see Nb is very small, 0.8 in comparison to 47. That is why we ignore Nb everywhere. So now when we use using Raoult's law, what we can write, P naught A minus PA divided by P naught A. So this is equals to chi B, means XB. So this I can write, XB can be written as NB divided by Na plus NB. So put these values. So P naught is pure vapor pressure. Pure vapor pressure, it is given 23.8. So when I'm just putting these values, 23.8, PA we have to calculate, because you have to calculate the vapor pressure of the water from this solution. So we have to calculate PA. What is P naught A again? You can write 23.8. is equals to NB we have just calculated, it is 0.83. So it is 0.83 divided by NA plus NB, so 0.83 plus 47.22. So I can write 0.83 plus 47.22. So when we solve this right part, so again I can write it as 23.8 minus PA divided by 23.8 is equals to, when we solve this 0.83 divided by this value, so we get on it is 0.173. Okay, so from here we can calculate PA. So when we transfer this number to this side, multiply this number, and then we get the value of PA. It comes out to be 23.4. So now since it is pressure, so unit will be same, mm of Hg. Okay, now this is the first part, because we have to calculate vapor pressure of the water from this solution. So we have calculated vapor pressure of water from this solution. Now we have to calculate its relative lowering. So we can also calculate relative lowering. What is the formula of relative lowering? This is the formula for relative lowering. So we know P naught A is 23.8. So in order to calculate a relative lowering of vapor pressure, we can write 23.8 minus P. So now we know the value of P, it is 23.4. So divided by P naught, so again 23.8. So it will come out to be 0.23.0.4 divided by 23.8. So it will come out to be 0.0173 mm Hg. So this is the relative lowering of vapor pressure. So in this way we can solve this equation. This question is important. We will discuss all these examples once again in when we discuss Van 't Hoff factor. Okay, so solution is given. So it is 23.4 P, and relative lowering you can calculate, it will come out to be, this is the given amount is given, number is given, 0.0173. So in this way we can solve this question. Okay, second colligative property is a relative elevation in boiling point. Okay, so in elevation in boiling point, the first thing is to understand this graph. What is boiling point? So very first thing we should know what is boiling point, definition of boiling point. So boiling point of a liquid, it is the temperature at which the vapor pressure of the liquid becomes equals to the atmospheric pressure. So see, it is written 1 atm is written. 1 atm is what? Atmospheric pressure. So this is the line at which the pressure of a liquid becomes equals to the atmospheric pressure. That means this is the point which will define this boiling point of any liquid. Okay, so now this red line represents the pure solvent. So you can see this is the point at which pure solvent is having its boiling point. So we have assumed it is to be PB not represents pure. Okay, so when you add a little amount of solute into it, so now this green line represents the variation of vapor pressure of a solution. So this point again, because at this point only this point is touching 1 atm line. So this point again represents the boiling point of the solution. This is represented as PB, and if this is the axis of temperature, that means this is a lower temperature and this is the higher temperature. So that is why we say elevation in boiling point. That means this is the lower temperature, lower one, and this is higher. And this is the increase in temperature when we add any amount of solute into any solvent. So that is why it is called elevation in boiling point. Okay. Now it is represented as delta TB. So everywhere it is written, it is represented as delta TB. Delta TB represents the elevation in boiling point. Okay. Now delta TB is, it depends upon the lowering of the vapor pressure, because whatever amount of solute is going to be added, suppose we are adding more amount of solute into it, then vapor pressure will be even lower. So that means this TB, delta TB, is directly proportional to what? Delta P, means lowering of vapor pressure. If we are adding more solute, so lowering will be even higher and delta TB will be even bigger. Suppose you are adding just 1 tablespoon of salt and you are adding 10 tablespoon of salt. So when you change the amount of solute, lowering of vapor pressure will also change, and accordingly delta TB will also change. That means delta TB is directly proportional to what? This delta P. Okay. From Raoult's law, we know that delta P is what? Delta P is directly proportional to chi B. This is the statement of Raoult law. The lowering of vapor pressure is directly proportional to the mole fraction of the solute. So this is the first equation and this is the second equation. So what we can write, since delta TB is proportional to delta P and delta P is proportional to chi B, so can I write it as delta TB is directly proportional to chi B, because equation 1 and 2 are same. Okay, so same thing, if I remove this constant of proportionality, so delta TB, I have to put some constant K. Now it is chi B. Okay, again we have to do the same thing. Chi B is what? It is mole fraction of B. So mole fraction of B can be written as NB, Na plus NB. Now NB can be written as WB by MB, and WB by MB, and Na can be written as WA by MA, plus NB again can be written as WB by MB. So we are just putting these values. Again, same approximation I will use, since it is for dilute solution. Since colligative properties are defined for dilute solution, so I will neglect this value in the denominator. So WB by MB is very small in comparison to WA by MA. So I can write this equation again, delta TB is equals to K into WB by MB, and in the denominator I'm removing this value WB by MB, so it will be just WA by MA. So when I rearrange this equation, delta TB is equals to K into, I can write it as this part, WB by MB is what? Given mass by molar mass. So again I can write it as NB. And what is WA? So WA is weight of solvent. So WA. Okay, and now this, sorry, this is not WA by MA. This is not plus. It is WA divided by MA. So now this MA is in division, so it will come in multiplication. Okay, this part is very important. This is step. So delta TB is K into, now what is NB upon WA? It is number of moles of solute divided by mass of solvent. WA is what? Mass of solvent. And this is nothing but what? Molality. Number of moles of solute divided by mass of solvent. M, again MA is left, so it is MA written like this. That means this is the expression that we have till now. Delta TB is equals to K into this M into MA. Now what is MA? MA is a molar mass of the solvent. So solvent may be water, it may be anything. So if it is water, that means value of MA is 18. If it is any solvent, if you take it as alcohol, ethanol, it is 46. That means MA is what? It is also a constant value. And what is this K? K is again constant of proportionality. So when we multiply these two constants, we get another constant, and that another constant is called KB into M. Hence we get this equation. So in NCERT, this equation is written directly. delta TB is equals to Kb into m. But Kb is multiplication of this constant and molar mass. And what is m? M is molality. Now, this Kb is very important. Kb is called, molar elevation constant. This Kb is called molar elevation constant. And the second name for this is molar ebullioscopic constant. Molar ebullioscopic constant. But molar elevation constant is sufficient. And every second or third year we get this definition, that we get this question in multiple choice, that what is the unit of Kb. So this part is very important. Unit, you can write, unit of Kb is Kelvin kilogram per mole. Kelvin kilogram per mole, mole inverse per mole. So this is all we need to know about this elevation in boiling point part. Okay, one more thing that we can relate from here is this delta TB is what? Elevation in boiling point. So you can see elevation is boiling point is directly proportional to what? M. M is what? Molality. And molality can be written as what? Number of moles by mass of solvent. So M is expression of NB into WA. That means delta TB is directly proportional to what? NB, number of mole, not nature of mole. So that is why elevation in boiling point is also a colligative property, because it is dependent on number of moles, not on the nature. Okay, unit is, it becomes very important. Now coming to the second part of this elevation in boiling point is determination of molar mass. So I will write it separately. Determination of solute from delta TB means from elevation in boiling point. So what we can write, MB is molality of a solution. We have written delta TB is equals to Kb into M. So Kb into M can be written as, molality can be written as WB, or I will write the previous step first. Molality can be written as number of moles divided by mass of solvent in kg. So if it is not in kg, that means we have to divide it by 1000 if it is in grams. So here you can write it is in grams. Okay, so when we rearrange it, so it becomes Kb into Nb. Now it is can be written as Wb by Mb divided by Wa. This is in grams, and divided by 1000. So when we rearrange this, we get Wb by Mb into, we get 1000 here divided by Wa. So this is the formula. When we rearrange it, we get, now this take this Mb to the other side. So with respect to Mb, if I write it, so it becomes Mb is equals to Kb into Wb into 1000 divided by Wa into delta TB. So this is the formula which is very important for calculation of molar mass. This formula is very important. Now again, what you can derive, delta TB is what? This is colligative property, elevation in boiling point, and Mb is what? Molar mass of solute. Again you can see this molar mass is varying inversely with colligative property. Molar mass varies inversely with colligative property. So this formula Mb is equals to Kb into Wb into 1000 divided by Wa into delta TB. This is very important for numericals. Okay, so now you can see these are the examples of elevation in boiling point. So while cooking, when we add salt in water, so when you cook Maggi, pasta, even food pulses, so The moment we add non-volatile salt NaCl, so what happens? It increases, its boiling point. So there is an elevation in boiling point. That means now that particular food is, cooking at higher temperature. Similarly, pressure cooker also works on this mechanism. So when steam is trapped inside the vessel, so it raises the liquid's boiling point, and which ultimately reduces the cooking time. This part is very important. Engine coolant. So in cars we have radiator. So engine, in that radiator we use a coolant. That coolant is mixture of 50% of water and ethylene glycol. So when ethylene glycol mixes with water, it increases the boiling point of water. Otherwise water would evaporate, or it starts boiling at 100 degrees Celsius. So when we add 50% ethylene glycol, so that boiling point increases to 107 or 110 degrees Celsius, so which prevents that vehicle against overheating. So these are some common examples of elevation in boiling point and how we are using it. Okay, so this part, numerical one, boiling point of water at 750 mmHg is 99.63 degrees Celsius. How much sucrose is to be added to 500 gram of water such that it boils at 100 degrees Celsius? Okay, so water means pure water at this pressure boils at 99.6 degrees Celsius. So the question is, how much sucrose is to be added to 500 gram of water so that it boils at 100 degrees Celsius? So we have to calculate amount of sucrose. So let us assume that mass of sucrose required is mass of sucrose, because we have to calculate it. So mass of sucrose required, that means what is required is WB. So we have assumed it to be WB. We know the mass of solvent. Mass of solvent, it is given 500. So this is nothing but WA. So WA is given 500 gram. Fine. Now what else we need? We need that molar mass. So we have this value, molar mass is given to us, which is 342, because it is written molar, how much sucrose is to be added. So molar mass of sucrose, formula of sucrose is C12H22O11. So when we calculate this molar mass, so MB molar mass would come out to be 342 gram per mole. Okay, and what else is given? Elevation we can calculate from here. So delta TB, what is the value of delta TB? So it should boil at 100 degrees Celsius. Right now it is boiling at 99.63. So calculate the difference. So when we calculate the difference, it comes out to be 0.37 degrees Celsius, because it is given in degrees Celsius. So either you take degree Celsius or Kelvin. This is important. When we take the difference is same on both scale, whether it is Kelvin or degree Celsius. Suppose if I say right now temperature is 300 Kelvin. So if it is 300 Kelvin, that means it is what, 27 degrees Celsius or 300 Kelvin. Suppose if I say there are some chances of rainfall, and tomorrow this temperature will increase by 4 units. So if I am saying 4 units, that means this would become 31 degrees Celsius and this would become 304 Kelvin. So whenever we talk about difference, this difference is same on both scale. But when we have to convert it, so we have to always use Kelvin, because Kelvin is the SI unit. Temperature is same on both scale. So MB we have calculated 342. So just put these value. TB is also 0.37 degrees Celsius or Kelvin. So just put these values, and what we have to calculate? We have to calculate WB. So this is the aim, or this is required. So we know that formula is delta TB is what? KB into WB into 1000 divided by this is WB into MB. So when we rearrange, because we have to calculate WB, so rearrange this formula with respect to WB. So we get WB, this is delta TB into WA into MB divided by KB into 1000. KB into 1000. So just put these values. Delta TB is what? 0.37. WA is 500 mass of solvent, and this molar mass is 342. Divided by KB is 0.52. I think it is not given in the question. Okay, so you can write it. It should be given in the question. For water, the value of KB is 0.52. For water, the value of KB is 0.52, and what is the unit? Kelvin kilogram per mole. So KB is 0.52 into that 1000. So when you solve this thing, this weight of solute, it comes out to be 121.67 gram. So this is the result. That means this much amount of sucrose is to be added to 500 gram of water in order so that it boils at 100 degrees Celsius. Okay, so one question, assassin reason, which I found this is a good question. The boiling point of pure water is always higher than boiling point of solution. So whether assassin is correct, boiling point of pure water always higher than the boiling point of the solution. Okay, reason is the vapor pressure of the solvent decreases in presence of non-volatile solute. So this one is correct. Reason is correct. But what about assassin? The boiling point of pure water is always higher than. Okay, so this word always, so wherever you come across such word, only, always, so these cases represent extreme scenario. That means only this part is followed, or it is always followed. So wherever these types of words are written, so there are high chances that it would be incorrect. But we have a reason also. The boiling point of pure water is always higher than the boiling point of the solution. No, it is not always, because we have discussed about negative deviation in Raoult law. We have discussed about solutions showing negative deviation. Suppose these types of solutions where AB interaction is higher than AA or BB. So these types of solution, pure water, the vapor pressure of solution or boiling point of solution will be even higher than the pure solvent. So I think assertion is incorrect, but reason is correct. Okay, so this solution is also given. So it is 122. Okay, so what about this? Assertion is false and reason is true. So reason assertion is false because of negative deviation cases, and also these types of word, they always represent extreme case. Third part, depression in freezing point. So it is represented as delta TF. Again same thing. First understand this graph. So what is freezing point? Freezing point of any substance is the temperature at which solid and liquid phases of the substance coexist. So it is the temperature at which solid and liquid phases, both of these two are coexist. So it is defined as the temperature at which its solid and liquid phases have same vapor pressure. So this axis represents vapor pressure. And what is freezing point? This is freezing point. So it is a point where the vapor pressure of its liquid phase, which is liquid solvent and solution, these two are same. So you can see this is the frozen solvent, solid solvent. So this is this part, brown line, this represents solid part, and this green line represents liquid solution. So you can see this is the point where vapor pressure of both this liquid and this frozen solvent are same. So this point represents the freezing point. Okay. Second thing is, this is liquid solvent, pure solvent, pure solvent. So this red line represents pure solvent. So you can see this point is freezing point for pure solvent. So I can write this temperature as delta TF naught. Naught again represents pure. This is for pure. When you add a small amount of solute into it, now it has become solution. So you can see at this point, because this is the temperature where pure this solvent is, be it water or anything else. So at this point, pure liquid is having freezing point, but at this point, the solution is in liquid state only. So that is why it is called depression. So where it is becoming solid, it is becoming solid at slightly lower temperature than the freezing point of liquid solvent. That means this point, this deviation from this point to this point, this is the depression, and that is why this difference is represented as delta TF. That means depression in freezing point. So whenever we add any solute into any pure solvent, so there is a decrease in its freezing point. That means it freezes at slightly lower temperature than its freezing point of pure solvent. So it is uh, depression in freezing point. So same thing, we can write this delta TF. If you increase more solute, so there will be more lowering of vapor pressure. That means delta TF is directly proportional to delta P. Second part, Raoult law, delta P is directly proportional to chi B. So that means we can write delta TF is directly proportional to chi B. Same process which we have done for the previous colligative property, elevation boiling point. So delta TF is directly proportional to what? This chi B. So again I can write delta TF is directly proportional to, if I remove this sign, so let us remove this sign. So when we remove this sign, it becomes K into chi B. Okay, so again I can write delta TF this K into, now this XB can be written as what? NB upon Na plus NB, Na plus NB. Now same assumption, because the solution, this colligative property is defined for dilute solution. So because it is dilute, so I will remove this number of mole of B. It is very less. So I can write delta TF is equals to K into NB divided by Na only. So again, if I write this expression, so I can write NB is what? WB by MB. So I'm writing MB here, and this Na is what? WA upon MA. So when again we rearrange it, so WB by, sorry, this WB by WA is what? M, molality. So when we again rearrange this equation, so it is written from, that means next part is written here. That means delta TF is directly proportional to molality. So again, if I remove this sign of proportionality, so we get KF, and this molality is again represented in form of WB by MB. So finally, the same process has to be followed. We get this equation. This delta TF is colligative property. This is molar mass. So again, you can see this varies inversely. That means colligative property is varying inversely with the molar mass of the solute. In every colligative property, the most important, I would say, part is to understand, interpret this graph. If you are able to interpret this graph, you will be in much better position to define everything. Okay, so let us move ahead and discuss some example of freezing point depression. So there are various examples of freezing point depression. So in mountains, wherever the temperature is very low, so these roads, because of this freezing of water, so these roads have a lot of ice on the, a lot of ice gets blocks this road. So what we do is, salt is poured or salt is spread on these roads. So why this road salting is done? So when we add salt to icy roads, so the freezing point gets depressed. That means freezing point of water gets lower. Suppose temperature in Ladakh is 0 degrees Celsius or even lower than that. So if it is 0 degrees Celsius, water will freeze immediately. If we are adding this salt, spreading salt on the roads, what will happen? There will be depression in freezing point. That means now this ice will melt somewhere minus 20 degrees Celsius. So that means freezing, this formation of ice on road will take longer time. So we can prevent, icing of the road. Second part is making ice cream. So when you normally make ice cream, so it freezes at 0 degrees Celsius. But when this vessel, means the chamber in which that ice part is kept for freezing, that chamber is having a lot of salt, means surrounding that particular vessel, salt is filled. So what happens when salt is there? So that particular ice, it freezes at even lower temperature, depression freezing point. Suppose water freezes at 0 degrees Celsius, so if you are adding again salt, so it will freeze at minus 20 degrees Celsius. That means that ice formation will be even better. If it is freezing at minus 20 degrees Celsius, it will be even hard, even better stability. So because it is freezing at lower temperature, so again it is an example of depression freezing point. Now just like we discussed elevation in boiling point, so that car coolant, it prevents radiator of the car even the temperature, if the temperature is high. So because it is having elevation in boiling point, so it boils at 110 or 107 degrees Celsius. Similarly, if the gates or the doors of the car is filled with water, so if you visit any mountain range, so it will freeze at 0 degrees Celsius. But if that car window or radiator is filled with ethylene glycol, so because you are adding solute into that water, so there is a depression freezing point. So because of that depression, that water does not freezes at 0 degrees Celsius, but it freezes at somewhere around 20 or 27 degrees Celsius, minus 27 degrees Celsius. That means there is a depression in freezing point. So that radiator, it doesn't freeze, and if it doesn't freeze, so it prevents it from getting burst or prevents it from getting cracked. That is the uh, purpose of adding coolant or antifreeze car radiators. And the main ingredient that is used is ethylene glycol. So 50% of water and ethylene glycol is used for this purpose. Okay, so now coming to the numerical part, let us discuss one question. We will cover this part, numerical part, in detail when we discuss Van 't Hoff factor. So calculate the mass of ascorbic acid. A formula is given to be dissolved in 75 gram of acetic acid to lower its melting point by 1.5 degrees Celsius. That means we have to decrease the freezing point by 1.5 degrees Celsius. That means delta TF is what? 1.5. So even if it is degree Celsius, or the difference is always same. Okay. So we have to calculate what? Mass of ascorbic acid. That means WB is the aim of this question. We have to calculate this. Okay, molar mass of ascorbic acid we can calculate because formula is given. So when you put this C6H8O6, so molar mass, it comes out to be 176. So MB is what? 176. Okay, I think mass of solvent is also given 75 grams. So we can also write WA, mass of solvent, it is 75 gram. Depression is 1.5 degrees Celsius. Fine. So just put these values in formula. Delta TF is equals to KF into WB into 1000 divided by MB into WA. Now you have to calculate what? WB. So rearrange this formula with respect to WB. So WB is equals to delta TF into MB into WA divided by KF into 1000. So this will come out to be, put these values. So delta TF is 1.5 into MB is 176 into WA is 75 divided by KF is given. KF for water is 3.9. So 3.9 Kelvin kilogram per mole is its unit. Very important. 1000. So this is 1000. So when you solve all these things, WB, it comes out to be 5.08 gram. So that is the amount of ascorbic acid that is to be added to this solution. Okay, so solution is there. 5.08 gram is the correct answer. This question has been asked in CBSE 2020. I think one more time, I think in 15 or 16 maybe this question was there. Important question. Okay. Okay, this question, why is ethylene glycol and water mixture is used in car radiator in cold countries? So just I explain this example. Ethylene glycol, it lowers the freezing point of the water. Due to this, coolant in the radiator will not freeze. Otherwise, a radiator will burst due to freezing of water. You can also write pure water freezes at 0 degrees Celsius. But when we add ethylene glycol, so it freezes, even lower than minus 20 degrees Celsius. So somewhere minus 27, 26 degrees Celsius, it freezes. So this mixture, water ethylene glycol mixture, it prevents those car radiators to get freezed, and hence it prevents it from getting burst. Okay, fourth colligative property is osmotic pressure. So before we start osmotic pressure, we must know what is osmosis. So osmosis, if we separate any two components, solvent and solution, from a semi-permeable membrane, in shortcut we call it as SPM. Semi-permeable, as the name suggests, that means this membrane is semi-permeable. So only a certain type of particles can pass this membrane. Not all the solid particles can pass. Only some limited type of solids can pass. So the solvent molecules will flow through the membrane from pure solvent to the solution. That means solvent molecules can flow through this membrane, but no solute can pass through this. So this process of flow of solvent from a region of its higher concentration to a region of its lower concentration is called osmosis. But this osmosis, this requires what? A membrane. So the excess pressure, this part is very important. Very, easiest definition of osmotic pressure. The excess pressure required to just prevent osmosis is called osmotic pressure. So suppose if I write it in this way, so if I separate these two chambers by semi-permeable membrane, this side I have solution, this side I have pure solvent. So from pure to solution, these solvent particles will migrate. Okay, so suppose this chamber is airtight, packed, and this side I have vacuum. So if I apply pressure, some pressure using piston or any external agent, if I apply pressure to this side, and the pressure of means that external pressure should match this pressure, that the process of osmosis stops. So that excess pressure which is applied from external side in order to stop the process of osmosis is called osmotic pressure. Okay, so this is what written here. The excess pressure required to just prevent osmosis is called osmotic pressure. Now, what are semi-permeable membrane? It is called SPM. So a membrane which only allows solvent molecules to pass. like it is made up of cellophane, parchment paper, and wall of living cells also. So there are various types of membrane. So since we are dealing with coordination chemistry also, coordination chemistry chapter is there. So this is a type of coordinate compound, copper ferrocyanide. So it is also used as SPF, copper ferrocyanide. Now what is osmotic pressure? Osmotic pressure of a solution is the excess pressure that must be applied in order to prevent osmosis, to stop the flow of solvent molecule through soluble membrane. Osmotic pressure, it is represented by pi. It is proportional to molarity, that is concentration of the solution at a given temperature. Okay, so what we can write from here is, since this osmosis is uh, varies directly with the concentration, so I can write here uh, one equation that we know, PV is equals to nRT. PV is equals to nRT, that ideal gas equation. So P is what? Pressure. So similarly we can write pi is also pressure, osmotic pressure. Pi V is equals to nRT. Okay, so when this V goes to this side, it becomes N by V RT. N by V is what? Number of moles divided by volume of solution. So this is nothing but molarity. So capital M into RT. That is why we get this expression, pi is equals to MRT. M is what? Molarity. And molarity is what? Concentration. So in some books it is also written as pi is equals to CRT. C is what? Concentration. And if you have to represent this C, so C is nothing but number of moles by volume of solution in liters. Okay, so we get this equation, pi is equals to CRT. Now these are the basic definitions that we should know. Isotonic, because one numerical is there based on this definition, isotonic. So what are isotonic solutions? The iso word means same. So two solutions, iso means same, and this tonic word comes for osmotic pressure. So two solutions having same osmotic pressure at a given temperature are called isotonic solutions. So whenever, okay, there are one more term, hypertonic. It is written hypertonic and hypotonic. So if the osmotic pressure of two solutions are same, then those two solutions are called isotonic. But if it is not same, so if it is not same, so the solution having higher osmotic pressure is called hypertonic, and the solution having lower osmotic pressure is called hypotonic. If it is same, it is isotonic. Okay, so if it is isotonic, that means these two numbers are same because osmotic pressures are same. So what is pi is equals to this part, we get pi is equals to means CRT. So when we write, we can also write this CR E1 is equals to CR. Okay, so if temperature is same, so temperature has no significance, only concentration varies. So C1 RT is equals to C2 RT. R is again universal gas constant. Temperature, if it is constant, so temperature has no role to play. That means what? C1 is equals to C2. That means if two solutions are isotonic, then their concentration is also same. Concentration same, that means what? Given mass by molar mass is also same. So we get this relation. W1 by M1 is equals to WB by W2 by M2. Based on this relation, we have one numerical. We will do this numerical later on. Okay, now this part comes to the last part of this colligative property, reverse osmosis and water purification. So we all know what is osmosis. Osmosis is a flow of what? Flow of solvent from high concentration to low concentration, and that only of solvent, not solute. Okay, what is reverse osmosis? It is just opposite of this. So suppose we have two components, solution and pure solvent. So if from solution side, because generally what happens, this process is osmosis, if from solutions solvent side anything coming to the solution side. But if we apply lot of pressure to solution side, very huge pressure on solution side, so what will happen? This osmosis will not only stop, but it will occur in opposite direction, because osmotic pressure is what? It is amount of pressure to stop osmosis. So if that much is the pressure, then osmosis will stop. But if external pressure is even higher, then the process will start occurring in reverse direction, and hence we say this is reverse osmosis. So what is the definition of reverse osmosis? So it is the flow of solvent from solution side to the solvent side, or you can say it is the flow of solvent from low concentration to high concentration. Generally what happens, we have high concentration to low concentration, but osmosis in this case, it is from low concentration to high concentration, because solvent is high on this side. So this is reverse osmosis. So we can define direction of osmosis can be reversed if external pressure which is applied is much higher than osmotic pressure. So this process is called reverse osmosis, and reverse osmosis is used for the desalination, means to purification of water. Now just look at this setup. So this is salt water, so or you can say this is tap water, so normal water that we get. So this is tap water. If that pressure on this side pressure is so high, this is SPM, this line is SPM, so it will not allow flow of solute. Solute means what? Whatever ions we have, metal ions, or impurity, or sand, anything. So any type of impurity is what? Solute. And whatever in this tap water or salt water, whatever is the amount of water is there, that means pure solvent, that is allowed. So only flow of water is allowed, और इस मेम्ब्रेन पे जितने सारे मतलब सॉल्ट्स हैं या आयंस है वो सब यहाँ पे डिपॉजिट होते रहेंगे, उनका फ्लो not allowed. Only water can move from this side to that side. Hence we get fresh water this side. We get fresh water this side, and we can use it. So this is the working mechanism of reverse osmosis. That is why after some time this membrane it expires. Why? Because lot of ion deposition is there, lot of metal ions are deposits on this side. That is why this membrane has to be replaced every 4 or 6 months, depending upon the salinity of the water or impurities in water. That is one part, membrane has to be replaced. Second part, now some minerals are there in water which are essential for our growth and proper functioning. So reverse osmosis, in this process those essential metal ions are also being stopped, they are not allowed to move. That is why earlier these RO systems which were there, so because of that this water is just water having no iron, no magnesium, no zinc, no calcium, nothing, no sodium, potassium, only water. That is why some cases emerge that people, those who consume this water, they are having some sort of deficiency of ions in their body. So that is why later on these brands, they introduced TDS. TDS is what? Total dissolved solids. So they have, now we have TDS controller in any water RO system, we have TDS. So what is TDS? TDS, after getting this fresh water, TDS releases essential ions like metal ions, like zinc is important, sodium is important, magnesium important. So all these ions are being again injected into the water to make it healthy and to make it full of essential minerals. So now we have TDS controller, reverse osmosis. Okay, so this is all about reverse osmosis and purification of water. There are various examples. So I think 2 or 3 days ago in my YouTube short, I have also discussed one example that why plants, they convert normal sugar or glucose into starch. So plants, they convert this carbohydrate, sugar, glucose into starch. Why? Because if it is only glucose, so what is the molar mass of glucose? It is 180. And what is the molar mass of starch? It is in thousands, 20,000, 40,000, depending upon the size of the polymer. So can you imagine 180 molar mass and 20, 40,000 molar mass? That is why plants convert this glucose into starch in order to increase molar mass. And when we increase molar mass, what relation we have derived? Molar mass is inversely proportional to colligative property. So when water, this plant or trees, they increase the molar mass, that means they are what? Decreasing colligative property. So when they decrease colligative property, so what they are actually decreasing? They are decreasing the osmotic pressure. And when osmotic pressure is less, that means amount of means inflow of water is less. That is why if this, if it remains as glucose only, glucose, that means in 40,000 of mass there will be so many glucose molecules. Again, colligative property depends upon what? Number of particles. So if any plant does not convert this glucose into starch, it is only glucose, so a lot of glucose particles, glucose molecules are there. So a lot of particles, that means colligative property depends upon particle number only. So a lot of osmotic pressure will be there, a lot of water will be there in the roots. So ultimately what will happen? It will burst, and it is not good for the, if roots start retention of water, then life of trees will not be that much. That is why these plants, they convert glucose into starch. So colligative property, or conversion of this, nature actually, they are the good chemist, they are the good physical chemist, so they know how to utilize science for their growth. Okay, so same thing here also. Example of osmosis, plant cell. So we all know about turgor pressure. So if solute, hypotonic means low solute outside. So if solute is low outside, so what will happen? Water will start entering the cell, and cell becomes turgid, that means it will swell. Second example, if you know if the solution is isotonic, means the concentration is same inside the cell and outside the cell, so what will happen? Osmotic pressure will remain balanced, and it is good for the health of the plant cell. So this is the ideal condition to balance osmotic pressure. This part is most important. So whenever we go for any intravenous injection, IV, so what happens? Doctors use 0.9% weight by volume saline water. Saline water. So why only this concentration, 0.9? In the first slide of concentration term, I have explained this. 0.9%, because that is the concentration of our blood cell. So if solute is too low, what will happen? Water will start entering to the blood cell, and it will swell, and ultimately that blood cell will burst. What is the ideal condition? That this concentration should remain constant. That means if it is isotonic, then we will have a healthy cell, healthy blood cell, because osmotic pressure inside the cell will prevent the net inflow of water, and cell will remain normal. So that is how these osmotic pressure plays the role. And we have just now discussed the working mechanism of reverse osmosis in water purification. So water, it flows from pure water to the solution due to osmotic pressure. So when external pressure applied is very high, so we get reverse osmosis. So this is the equation for osmotic pressure. Pi is equals to CRT or MRT, and this is I. I is what? Van Hoff factor. So this Van Hoff factor we will discuss in the last video of our this series, and in that we will only cover Van Hoff factor, that too in great detail. So again, there are various examples. This I have just explained in my YouTube short also, and even I have explained it right now. The conversion of glucose to starch. in order to prevent the osmotic pressure and water retention. Reverse osmosis, we all know that this membrane, it restricts the flow of these solutes or any other metal ion, and what we get only fresh water. So these are the examples of osmotic pressure and osmosis. This is the question which is very important from this part of osmotic pressure. So a solution containing 15 gram of urea, molar mass of urea is this much per liter of the solution in water has same osmotic pressure. That means it is isotonic. So if it is isotonic, then we have just derived, if it is isotonic, that means W1 by M1 is equals to W2 by M2. So what we have to calculate the mass of the glucose present in this one. Okay, fine. So we can directly, this question is important. I think this has, this was there in board exam thrice. After 16 also it was there, but two times it is written. So the solution is already given. So this we just have, derived W1 upon M1 is equals to W2 by M2. So you will get the mass of glucose as 45. So solution is given, just go through it and you can get the answer. Second question is, how is it measurement of the osmotic pressure is more widely used for? Okay, so this question was there, 2026 is written here, this year, just 2 or 3 months ago. So how the osmotic pressure is more widely used in determining molar mass of macromolecules. Macromolecules means big size molecules, like we have proteins, starch, for which molar mass is more than 10-20,000 in, and then elevation boiling point. That means how osmotic pressure method is better than elevation boiling point or depression in freezing point. When we are calculating molar mass of macromolecules, means big size molecules. So what is the difference? We have seen delta TB is what? KB into M. Delta TF is what? KF into M. But what is pi, osmotic pressure? That is MRT. Okay. So here we have a small m, molality. But in osmotic pressure, what we have? Molarity. So that is the difference. First difference. In other colligative properties, we use molality, whereas in osmotic pressure, we use molarity. That means it is measured at, second advantage is it can be measured at, room temperature. So osmotic pressure method is important because it can be applied at room temperature, whereas for elevation boiling point we need some high temperature. For depression freezing point we need minus or 0 degrees Celsius, but this setup can be done even at room temperature. So that is the first advantage. It is written osmotic pressure is measured at room temperature. Second advantage, compared to other colligative properties, its magnitude is large even for very dilute solution, because if you solve the questions of elevation boiling point or depression freezing point, temperature is somewhere around 0.3 degree, 1 degree, 2 degree. But for osmotic pressure, the magnitude of colligative property is large even for very dilute solution. Third advantage, which of course it is mentioned in the question, but you can write, it is useful for calculation of molar mass of solute for macromolecules. Macromolecules means proteins, or we have starch or polymers, because for them molar mass is generally more than 10,000. So it is generally greater than 10,000 also. So that is why this method becomes very important. Which statement of the following is false? So units of atmospheric pressure and osmotic pressure are the same. So we have to find which statement is false. In reverse osmosis, solvent molecule move through semi-permeable membrane from a region of lower concentration of solute to a region of higher concentration. So I think this is the incorrect. Third one is, the value of molar depression constant depends on the nature of solute. The molar depression constant depends on the nature of the solvent. Relative lowering of water pressure is dimensionless quantity. Okay, so option B. Reverse osmosis, solvent molecule move through semi-permeable membrane from a region of lower concentration. No, it moves from higher concentration of solute because it is reverse osmosis of solute. This part is very important. So it moves from higher concentration of solute, that means saline water, to lower concentration, that means pure water. In pure water, concentration of solute is less or zero. Okay, so it moves from higher concentration to lower concentration, not from lower to higher. So option B is incorrect. These are the basic definitions we have discussed. Reverse osmosis, isotonic we have discussed, hypotonic we have discussed, hypertonic we have discussed. These two are new definitions. Isomotonic, let's see, when two isotonic solutions are separated. When two isotonic solutions are separated by SPM, no osmosis occurs. So this is a new definition. You know, osmotic solutions. Okay. Second new definition is plasmolysis. So when the cell is placed in hypertonic solution, the fluid comes out of the cell due to osmosis, and as a result, the cell material shrinks gradually. This process is called plasmolysis. So bio students must be familiar with this part. So this is just the summary of whatever we have discussed. All four colligative properties.
Please don't forget to like and share this video and subscribe to my channel. Thank you so much.